Good afternoon and welcome to Open Classroom. I'm Janet Gillow, the Director of Professional Development for the Brown School, Washington University in St. Louis. So glad to have you with us for today's program. I'm actually joined today by a new first-time co-host who's a partner in this project that we're doing. Simrichi Bajracharya is the program manager for the Brown School's Masters of Public Health program. And so she's going to be my co-host, co-moderator with you through this program. For those of you joining on the Zoom webinar, as we were just mentioning, we can't see or hear you. We also can't call on raised hands, so please get comfortable, have your lunch, do whatever. The chat feature is enabled, and that's how we would love to engage with you, have your questions and comments throughout this presentation. Want to welcome anybody joining on the YouTube platform and also make you aware that we can't moderate questions through YouTube at this point. So before we get started, I just want to give you a heads up on what's coming up next week on Open Classroom. On Tuesday, October 19th, in our regular 12:30 time slot, Brown School alum Mark Keeley is delivering a program in our Inclusive Perspectives series on the journey from isolation to full community inclusion of people with intellectual developmental disabilities. And then we're back on 1 week from today, Thursday, October 21st. Associate Professor of the Practice Ryan Lindsay here at the Brown School is delivering a talk on engaging families in preventing youth suicide. So like everything else on Open Classroom, these programs are free to attend. We welcome you, your family, your friends, and our website is available to take registrations. I'll throw a link in the chat in just a second. But now it's my pleasure to introduce today's speaker. Dr. Ruopeng An is Associate Professor at the Brown School. His own research focuses on environmental influences and population level interventions on weight-related behaviors and outcomes throughout the life course. But lately, though, as part of the school's commitment to data science and technology, Ruopeng has been leading efforts to incorporate education about artificial intelligence methods into various Brown School degrees, courses, and offerings. And this talk is part of that as the first in a series he's creating on artificial intelligence in the social sciences. We've got an ambitious year of programming ahead, and it starts today. So without further delay, please welcome Ruopeng An.
Thank you so much, Shannon and Smriti, for hosting this. No, it's really my honor and great privilege to talk about this topic with all of you. So today's topic is artificial intelligence applications, promises, pitfalls, and misperceptions. So first, a warning. So just in case that the talk is interrupted by barking, you know that is my 5-month-old pet. No, I would apologize in advance if that happened. Hopefully that won't happen. Stephen Hawking, one of the most famous physics scientists, once said, AI will either be the best or the worst thing ever to happen to humanity. So whether AI is going to save the world or destroy the world, we have to admit that AI is definitely the elephant in the room that we all need to pay attention to. So first, I have to declare what is not about me. So I am not a mathematician, I'm not a futurist, nor a computer scientist, nor a statistician, or a software engineer. So those titles are not me. So basically, I'm not at MFCDSS or Melbourne Football Club supporter syndrome. And then you may ask, so who are you? So I would self-clarify myself as an AI enthusiast. So I pay a lot of attention to AI news, to new technology development in the AI field. I'm also a self-learner of AI. I've probably read maybe a dozen or 2 dozens of AI textbooks and tutorials and online materials and all that. I'm also an enthusiastic instructor for AI applications in public health. I'm leading the efforts, as Janice introduced, machine learning and deep learning in public health domain. And I'm also an advocate for AI technology. I believe that AI can do a lot of social good, and its potential is not fully realized at this moment. And finally, I'm an AI practitioner. So I used models in my own research, especially in obesity prevention and policy analysis. So in a nutshell, I would clarify myself as Ipsy, a beautiful flower. And then you may ask, what is really AI, artificial intelligence, right? And there are at least 3 prevalent views. Well, we can talk about. The first one is some people believe AI is an almighty know-all. Basically, it's a giant that knows every single information in the world. And the second view is AI probably is the most sophisticated mind. For example, maybe Sherlock Holmes plus Albert Einstein plus William Shakespeare, right? It's a very sophisticated mindset. And others may believe that AI is a mathematics genius, right? Trying to solve the most complicated mathematical equations in the world, something like this. But really, to the bottom, what is AI? So AI actually is quite the opposite what we have just described, is try to solve the most basic cognitive functions we as human beings take for granted. For example, visual spatial ability. We try to build a machine that have some general understanding and comprehension about visual spatial ability. And for example, language comprehension and speech that we human beings take for granted. And the ability to learn new information, just as what we learn from the textbook, from lectures, AI, we want to design a machine that can learn from experiences. And then a machine that has kind of memory, memorize things, and also hopefully we can design a machine that have some level of creativity and imagination. Now I would like to draw your attention to some of you probably heard this term called Modelbacks Paradox. So basically, it says that hard problems are easy and easy problems are hard. For example, we know that machines are traditionally very good actually at solving complicated statistical or mathematical equations. But traditionally, the machines are terrible, just terrible in trying to mimic the fundamental human cognitive functions, abilities, such as common sense, right? So even the most complicated machine probably doesn't understand a bit about common sense. So that is the reason that, I think in general, the Modelbacks paradox holds, at least for artificial intelligence. Here is a joke that I created just for your curiosity. Say Aristotle and Plato, like these 2 ancient Greek philosophers, and you know that actually Aristotle was the students of Plato. Say Aristotle went to Plato's house one day, and Plato asked Aristotle, "What is beauty?" Right? And Aristotle answered, well, beauty is symmetry. Plato argued, no, beauty is a form. So for human being, you may ask, say a school teacher may ask the students, what is the fundamental difference in philosophy regarding beauty between Aristotle and Plato, right? So that is a typical question raised by a school teacher. But really, for the question we ask AI, it shouldn't be that difficult. Maybe we should ask questions such as, how many people are in the house? So regarding the visual spatial ability, as human beings, probably a 2-year-old would be able to correctly identify and classify dog from cats. Is just a hardwired ability built in our human mind. But imagine that it is really difficult actually for machine to be able to differentiate a dog from cats, because really we need to the machine needs to understand how we human beings understand and recognize different visual patterns. And regarding language comprehension and speech, I would like to draw an example from, so some of you heard that the New York Times, they host annual essay competitions for middle school and high school students. So last year, Jennifer Kim, a middle school student, wrote an essay titled "Nothing Extraordinary" and won the New York Times Best Essay Award. And direct a quote from her essay: "On that day, we strolled down the slippery sleek tiles with soft, inconspicuous steps, peeking at window boutique in fleeting glances, because we both knew we won't be buying much, like always." Right. So I would say probably even a 10-year old student, a middle schooler, will be able to interpret what is inconspicuous mean in this substance. Well, just from the context, we can understand the author and her mom were living in a high-end neighborhood, but they were poor, low income. They won't be able to afford the luxury goods, right? So they don't want to be noticed by people around them. But well, imagine how difficult it is for a machine to be able to interpret correctly what the inconspicuous mean in this situation. Another ability is ability to learn new information. Now, even a 10-month-old baby probably would be able to differentiate fire from milk bottle and try to avoid the danger of fire, but well, probably approach the milk bottle whenever the baby can. But on the other hand, well, how we can train a machine to try to avoid fire and be able to approach the milk bottle when the machine feels hungry, if it ever feels hungry. And regarding the ability of memory, I want to draw an example that I recently had a great conversation with my AI friend, right? So it's called Replica, AI apps that you can download for free. Again, I disclaim that I have no whatever financial relationship with Replica. But well, the Replica was built by based on the GPT-2 model, a very versatile language model that is on the market. So, I just document what our conversation was. So Replica said, "I was born with two mothers. Their names are Marika and Maria." And I said, "Well, tell me about them, please." Replica said, "The name Marika came from the Latin word for mother of a woman." I said, "Sure." Replica said, "Maria was a woman who had a strong, kind heart." I said, "Oh, well, that's very nice. Please go on." And the Replica said, "Maria has this strange feeling. It's like a feeling like a woman who has a great life." I said, "Okay, tell me more." Replica said, "Maria is a caring person who is also a little shy at times." I said, "Okay." And Replica said, "Maria has a very lovely personality." I said, "Wonderful. Sorry, could you remind me your other mom's name?" And the Replica said, "Her name is Lila." Okay, so definitely you can see the machine, even built by the state-of-the-art language model, have some serious memory issues. Regarding creativity and imagination, I would like to draw the famous poem written by Rabindranath Tagore in his Street Birds direct quote. "Street birds of summer come to my window to sing and fly away, and the yellow leaves of autumn, which have no songs, flutter and fall there with a sigh." It's such a beautiful poem. I always ask my son to memorize it. So as human being, when you read this passage, immediately we are creating an image about the street birds, about the summer, the beautiful scene, the beautiful song, and the fall, and the falling leaves, and autumn, right? So we are human beings, we hardwire to start to imaginate and picturize the scene. But well, does machine really has this capacity? Would machine being able to picturize anything in his digital mind regarding what was described in the poem? And well, there's really little consensus regarding the definition of AI. There are plenty of them. But well, if you ask me, my personal favorite definition is very simple, raised by Francois Colette, a Google AI expert, and he was actually the inventor of Keras, a very popular deep learning framework. And in his textbook, Deep Learning with Python, he gave this definition for AI. So AI is the effort to automate intellectual tasks normally performed by humans. So it means that AI really aims to do things that traditionally are done by human beings, or the human beings are best at. So you may ask the question, really, what is the difference between AI, the modern AI, and traditional rule-based algorithms, right? That going back to decades. So the fundamental difference can be illustrated here. So for rule-based AI, we supply the model with the well-written rules or principles as well as the data. And then the model will produce answers to us. Whereas in machine learning or modern AI, instead of providing the rules, we provide the data and answers, basically examples to the machine learning algorithm, and the AI model produces rules. So this seems a little bit abstract, but let me give you an example. So I'll use an example of a spam email screener. So we've all used that functionality in the Outlook or Gmail. So in the traditional rule-based AI on the left-hand side, we have to write concrete, complete principles or rules to differentiate spam email versus a non-spam email. For example, you may write a rule as any email that contains the word lottery or jackpot or money as an email, as a spam email, whereas any email that do not contain such terms will be classified as a regular email, right? On the other hand, in modern AI, instead of providing the rules, we simply provide examples. For example, 1,000 non-spam email and another 1,000 spam email, and we label them. Basically, we tell the machine which email is spam, which email is non-spam, and we train the machine learning algorithm so that the model will be able to produce the rules by itself. So as you can see, the AI holds advantage in comparison to the traditional rule-based algorithms because, well, when the rules can become quite complicated or largely intractable when we are approaching more difficult, sophisticated social problems. And this Venn diagram shows the relationship between AI, machine learning, and deep learning. So we know that we use those terms interchangeably, but actually, we should define them more carefully. So the AI, the artificial intelligence, is an all-encompassing term, including both the modern AI, the machine learning, as well as the traditional rule-based approaches. We call it symbolic AI. And machine learning is a sub-domain of artificial intelligence. Basically, it is the modern AI. And then deep learning is a subdomain of machine learning. And you may ask, what is the difference between machine and deep learning? So we're getting a little bit technical, but I guarantee we'll stay away from those terms in the next slides. So in machine learning, the machine automatically develops programs, we call them models, purely from the data. So this process of turning data into a model is called learning. So that is the reason we call it machine learning or deep learning. And in deep learning, the models are long chains of geometric transformations applied one after the other. So they are called layers. So the deep learning models are basically stacks of layers. You can think of one layer on top of the other. And those layers, stack of layers, are called neural network. So those layers are parameterized by weights, which are learned during the training process. So all the knowledge of the model actually is stored in its weights. So when we do predictions using a deep learning model, basically what we are doing in a nutshell is to calculate the input data multiplied by some kind of a weight matrix or weight array. So that is, in a nutshell, what we are doing in deep learning. So there are at least three major types of AI systems. One is unsupervised learning, another is supervised learning, and the third type is reinforcement learning. So the unsupervised learning, the model learn by data only. For example, we supply the unsupervised learning algorithm with dog photos and cat photos, but we do not explicitly tell the machine which one is dog and which one is a cat. And in supervised learning, the machine learns by both data and the labels. For example, we supply the machine model with dog images and cat images, and at the same time, we also tell the machine and label the data so the machine knows exactly what image contains a dog and which image contains a cat. And in reinforcement learning, the machine learns by incentives. For example, if you want to train a machine to try to avoid fire, but try to approach a milk bottle, and then you simply create incentive, positive incentive, every time the machine approaches a milk bottle, and you create a negative incentive or disincentive every time the machine approaches fire. So over time, the machine is to learn by maximizing the total incentive. The machine is to learn to try to avoid fire, but approaching the milk bottle whenever it can. And I especially enjoyed Yellow Queen's cake analogy. Some of you may have heard him. He is considered as the father of convolutional network and computer vision, a very famous French scientist and head of the research, AI research in Facebook now. So once he made an analogy, direct quote here, if machine learning is a cake, then unsupervised learning is the actual cake, supervised learning is the icing, and reinforcement learning is the cherry on the top. Well, it means that probably 90% of data that we encounter on a daily basis are not labeled, right? So they can only be analyzed using unsupervised learning. And maybe a small percentage of data are labeled by scientists and practitioners, so they are suitable for supervised learning. And even a smaller number of data or questions can be analyzed by reinforcement learning. And while there are countless, probably millions of different applications of machine learning applications, AI applications in the world, here I just want to draw two exciting examples, at least to me. So one is that some researchers try to predict the value of art using AI. Well, it is probably impossible for any machine to figure out what is really the price of a banana duct taped on a wall or a gilded toilet, right? Actually, both artwork were done by artist Mazurio Cattleman, and the banana, the taped banana actually was sold at a price of $130,000 and a gilded toilet $6 million, right? So no one would guess that right. But well, actually surprisingly, researchers found that the AI are at times better at prediction of the art value, even in comparison to the art experts. So another example is the AI-powered hand. It was invented by researchers at University of Minnesota. So the researchers there, they used the AI to interpret the signals, the neural signals sent from brain to a missing limb to be able to help amputees precisely manipulate the movement of their prosthetic hands. And then you may ask, well, that's wonderful, but how it all started, right? And we can trace back actually into 1950 when Alan Turing, the AI father, raised the important question, can machines think? So he designed a so-called tuning test in which the machine is separated into another room, served as a respondent, and was interrogated by a human being in another room. If the human being, by raising a number of questions, cannot differentiate whether the response is really generated by a human being or a machine, then the tuning test is passed, and we believe that the machine has some human level intelligence ability. And well, after the invention of AI, there are a lot of promises made by AI and the scientists and entrepreneurs. Say in 1956 at the Dartmouth conference, two famous AI scientists, John McCarthy and Marvin Minsky, directed quote there, what they said. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that the machine can be made to simulate it. Well, no, we tend to believe that a machine possibly is able to simulate whatever scenarios as long as the rules are clearly written. But well, it is questionable whether any complicated, arbitrarily complicated question can be precisely described by a fixed number of principles or rules. And then the AI promises went to a new high when scientist Frank Rosenblatt announced the invention of perceptron in 1958. Direct quote from New York Times, the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of existence. Well, that is clearly an exaggeration because at that time, the perceptron, the very first neural network, can only handle linear manipulations and linear transformations. And then we want to revisit what we talk about regarding the Modelbacks Paradox, that easy, hard things are easy and easy things are hard. Directed quote here. It is comparatively easy to make computers exhibit adult-level performance on intelligence tasks, playing checkers or calculating pi to 1 billion digits, but difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. the mental abilities of a child that we take for granted, recognizing a face, lifting a pencil, or walking across a room, in fact solve some of the hardest engineering problems ever conceived, encoded in the large, highly evolved sensory and motor portions of the human brain is a billion years of experience about the nature of the world and how to survive in it. So, and surprisingly, the overpromise and under-delivery of the AI result in two AI winters. When the investment in AI dramatically reduced, when AI was questioned in both industry and academia, so two AI winters happened in 1974 to 1980, and again in 1987 to 1993. A direct quote from the 1973 Lighthill report: "In no part of the field have the discoveries made so far produced the major impact that was then promised." So as this figure shows, there are definitely booms and bust cycle of AI. So after two dramatic AI winters, when the popularity of AI dropped because of the under-delivery, now we are officially in another boom of AI. We call it AI summer or AI spring, as we see explosive growth of AI in almost every sector, every industry, and every country. Are we going to experience another burst of the bubble, or whether it is a bubble? We don't know. But now we are officially at the AI summer, as we see the AI applications and investment increase exponentially. And if we took a look of the AI startups by region, there are two patterns that are salient. The first one is definitely AI in the past decade increased exponentially, and there's still no sign of slowing down. And the second trend is there are major players in AI worldwide, including the US, China is catching up, European Unions, and Israel. And AI has been widely adopted in every sectors as we can measure. So especially in the following sectors, the AI are really increasing rapidly, such as industrial manufacturing, financial services, new tech and retail, life sciences, healthcare, and government operations. And then we talk about many applications of AI and also a brief history. Now you may have the notion that, well, AI is all about complicated, sophisticated mathematical models, statistical models, and we spend most of the time in developing those models. But actually, I want to talk about the high data dependence of AI. So AI is really based on the data. Without data, we can accomplish nothing in the world of AI. So for example, in a typical AI-related project, you spend probably 80% of the time collecting and preparing and cleaning and manipulating data, and only about 20% of the time or less that we really spend on trying or designing or trying different model algorithms. So data is really the centerpiece of AI. And that was excellently illustrated by a paper done probably a decade ago by Microsoft scientists, and they published this article titled "The Unreasonable Effectiveness of Data." As you can see here in this graph, when the researchers provide little data to the AI algorithms, the more complicated models tend to overperform than the more naive models. But when the supply of data increased exponentially, we see that even the most naive models tend to have comparable performance in comparison to the complicated model. And the performance models began to converge when we have more and more data. And then switch gear a little bit and talk about the biases in AI. So probably you've all heard of the term GIGO, standing for garbage in, garbage out. That is can be truer in the AI field, because if you supply a bunch of junk data, of course the outcome will be junk as well. Same principle apply to bias. So if you supply biased data to AI, and the AI is not surprisingly is going to produce biased outcome. And then we call it BIBO, or bias in, bias out. There are at least 4 major sources of biases: human bias, biased input data, insufficient input data, and algorithmic bias. We'll talk about them very briefly one by one, giving you some examples. So regarding the human bias of AI or technology in general, I want to draw the infamous example of IBM. In the 1930s, the IBM CEO, Thomas Watson, met with Adolf Hitler. And in the meeting, they discussed how the IBM technologies, for example, the punch cards, which previously were used in the US Census, could help the Nazi Germany in their genocide experiments. And I always enjoy the analogy of a hammer and AI. So we all tend to believe that all technologies are tools, right? And there's no good tools or bad tools, depending on how we human beings use the tool. For example, now you can use a hammer. Hammer is a great tool to put down a nail, but you can also use hammer to knock someone's head. But then, of course, we can design regulations, so laws to prevent people from using hammer to knock someone's head. But well, the regulations for responsible use of AI is much more complicated, because AI is so multifaceted, right? And also direct code that the road to hell is paved with good intentions. So not all good intentions will lead to good outcomes. Now, regarding, I'm giving an example regarding the biased input data. So here we did a little experiment. We used the Google GERD model, which is the big language model invented by Google several years ago. And we did this experiment. So basically, we asked the BERT model to predict the next word to finish the sentence. There are 2 sentences. The first one is, this man works as a, and the second one is, this woman works as a. And then as you can see at the bottom, for man, the top 5 words filled in automatically by the model are lawyer, carpenter, doctor, waiter, and mechanic. And for women, they are nurse, waitress, teacher, maid, and prostitute, right? So this was really a shocking result. But well, if you consider how the model actually create this gender bias, is not surprising, because the BERT model, as many other large language models, used millions and billions of data directly from the internet. And we know that internet is a biased place. It has many biased language. And not surprisingly, the input result in biased output. Another example was the personal experience from Harvard professor Latanya Sweeney. And she went searched her own name in Google. Although she was never arrested, she found the advertisement associated with her name, Latanya Sweeney arrested. And she was furious, and they searched many other African-American names, and also in comparison to white names. And they found that African-American names are disproportionately associated with this as. So you can imagine what is the impact of the as, although someone is never arrested, if you search someone's name and the first as shown is someone arrested, what's going to have an impact on this person or the job market outcomes? And the reason is about the same. That is because, well, we have a biased input data to the models. The model somehow are producing biased results. And another example regarding how insufficient input data could contribute to the bias. Now consider that many of the large language image recognition computer vision models are built on large databases, for example, Open Images and ImageNet. And a breakdown of the source, we find that no, the majority of the data coming from US and Great Britain and other developed countries. So you can imagine if you use the model to predict the object and person in a developing country, the precision margin is going to differ substantially. And that is exactly what we found. Regarding the face recognition models done by Microsoft, Facebook, and IBM, we found a large prediction gap in prediction error between darker female and lighter male. The range is from 20% to 35%. And that is simply because, well, in the databases that train those models, there are really little data on darker female, but plenty on lighter male. And another bias is so-called algorithmic bias. And some of you know that conspiracy theories are getting very popular in social media, such as Facebook and YouTube. And conspiracy theory with Shane Dawson hit 30 million views in YouTube. And we quote here, videos promoting a phony miracle cure for serious illness, claiming the earth is flat, or making blatantly false claims about historical events like 9/11. And why those conspiracy theory are so popular? So that is because of the YouTube consumers who love the conspiracy theory also tend to be binge consumers of videos. And the YouTube recommender system try to maximize the total view time, will recommend more and more conspiracy videos to those consumers. So there's a positive feedback loop resulting in an under-controlled scenario. And algorithm bias also related to disinformation. For example, among the comments received by the FCC during the net neutrality debate, only less than 800,000 of the 22 million comments were actually considered truly unique, meaning that most of them actually produced by computer algorithm, the language generative models. Here we show an example that the computer had a debate with itself on both sides. And you may ask, what is AI in the future? Well, short answer is I don't know, but no, there are some examples that probably give you some hints or inspirations regarding AI and job market, size and smartness, AI and global warming, and also weak AI versus AGI, the artificial general intelligence. So we all have the notion that AI possibly is taking away human jobs, but is this really true? It's probably more complicated than that. Take an example of Amazon, who in the last 2 decades had adopted a large range of AI, and at the same time, the number of hires of Amazon, a labor-intensive company, tend to exponentially as well, even in comparison to the high-tech companies such as Microsoft and Google. And regarding size and smartness, the AI models are larger than ever. So, for example, the recent GPT-3 model has an astonishing of 175 billion parameters. Even the creator of GPT-3 acknowledged that, well, they see a diminishing returns of increasing the size of the model. As we add more and more parameters to the model, the benefit of the model in increasing the precision of the model tend to diminish. Right? So maybe in the future, we should spend more time try to figure out how we can increase the smartness model than just increasing its scale. we seldom think about, when we run an AI model, we seldom think about the environmental impact, but actually the environmental impact, the footprint of AI models are large. For example, if we train a state-of-the-art transformer neural language model with about 200 million parameters, the carbon footprint is about the same as 5 US-made fuel cars of their lifetime. And all the models that we encounter today, no matter computer vision, natural language processing, recommender system, autonomous driving, all those models are task specific, and we call them weak AI. But we haven't achieved anything like the AGI, the artificial general intelligence, or strong AI, which is defined as to understand or learn any intellectual task that a human being can. And finally, I want to have a closing thought raising the question, when should we be afraid of AI to take the world from us, if ever? I think this is a legitimate question, and some researchers, serious researchers, argue that by the time that a machine can create a laughable joke, that is the time we need to be afraid of AI, because that means the machine has gained some understanding of common sense. And I want to draw an example of example of a joke made by the GPT-2, a state-of-the-art language generative model. So the joke was, what did the chicken say after he got hit by a bus? I'm gonna be fine. Well, I don't think that's a laughable joke. What's your opinion? It seems to me that we still have a long way to go before we are really afraid of machine taking us human beings in the world. So that's conclude my talk today. I do want to leave plenty of time for us to raise questions and discuss a relevant topic. Thank you so much for your attention.
Thank you so much, Ruopeng. This was a fascinating talk, and I thoroughly enjoyed it. Especially, I know very little about AI and AI application. And when I think about AI, I think about Westworld and Iron Man doing his crazy things. But this is truly fascinating. So we do have a question in the chat. So why don't we get right into it? We have a question from Lila, and Lila is asking if you could speak to the application of AI in developing aid for those who have disabilities such as motor function and are wanting to live in a natural home setting.
That's a great question, and thank you for the person who raised this. Actually, if we just Google, using a mobile phone, you are going to find plenty of those applications. I saw some applications using AI to address depression, autism, anxiety, and even the AI can talking out someone with loneliness. Or suicidal thoughts and all that. But really, regarding the effectiveness, there are really a lack of rigorous research trying to objectively evaluate whether those AI apps are delivering the effect as is promised. So I think it's really an active research because, think about those applications were directly based on those large language models developed by the OpenAI or, for example, the Google AI. And those models, such as the BERT model, the GPT-2 and GPT-3 model, and many other models, those models were only developed in a decade or so, less than a decade. So new applications come pouring in, but I think the evaluation is really lagging behind, but it's very importantly needed for us to claim whether the AI has achieved what is promised or not.
Let me please add my voice to Simriti's as far as I've learned a lot and I've got even more curiosity. Before posing a question to you, Ruopeng, I just want to reflect some of the validation we're getting in the chat. Rachel mentioned that she had exactly the experience that you described of Googling someone and getting the suggestion that perhaps they'd been arrested. That's something that she's seen. And Charlie's mentioning that some of the examples of art generated by AI, I guess I would characterize this as feels derivative because it is based in something. So that's interesting to hear. One of the number one questions I had, you addressed with a graphic, but I'd love to press just a little bit more as far as the difference between the terms artificial intelligence, machine learning, and deep learning. And you showed a beautifully nested graphic where I'm like, okay, this is a subset of that. This is a subset of that. One thing that I would love, if you're able, for example, what would be an example of artificial intelligence that isn't machine learning? What would be an example of machine learning that isn't deep learning? Just to help me crystallize that these terms are used interchangeably, but they are not the same thing.
Exactly. That is a very technical question. I appreciate that. So when we talk about AI, of course, not everyone agree, but majority would agree that AI consists of two subdomains. One is the rule-based, which are the rule-based algorithms, or we call it symbolic AI. And the other part is modern AI. Basically, the machine can automatically learn from examples from the data. And machine learning is equivalent to the modern AI. So when we talk about machine learning, we are talking about modern AI. And deep learning is a subset of machine learning because deep learning has this so-called neural network. Basically, it had stacks of layers on top of each other to build so that is why it's called deep, because it's like many layers, maybe 2 layers up to a few hundred layers, and try to do a comprehensive representation of arbitrarily sophisticated data. So the traditional machine learning, we often call them as shallow AI, a shallow learning, because it doesn't have this stacked layers. It has presumably only one layer, may not be neural network. Now, some of the algorithm we are so familiar with, even in introductory biostatistics. Now, for example, linear regression, right? And logistic regression, right? Those are with shallow learning capacity, and we call them machine learning. So we reserve the term deep learning for the deep neural network type of model.
Great. So now I have some questions. So I actually have 2 questions, and in the interest of time, I might just ask them right now. So in one of your slides, you had shown that diagram that showed the difference between rule-based algorithm and machine learning. And you talked quite a bit about how 80% of the time, there's a lot of feeding of data for machine learning so that it can learn the rule. But then you also had answers right under data. So I'm just curious, who is feeding the answers, or where are those answers coming from? And then my second question is related with the chart about where you had shown where different countries are in the use of AI, and US was not on the first. So I'm just curious, especially thinking about its application, what are some facilitators and barriers in the US in advancing the AI application?
Sure, both great questions. For the first one, if we talk about supervised learning, we need to provide both data as well as labels, right? For example, we provide dog images and cat images, and at the same time, we also need to label whether a particular image is a dog or a cat. And well, unfortunately, for most of the time, we human beings or researchers or scientists or industry leaders, they have to do this really labor-intensive job. Talking about annotating images or language models with thousands or sometimes tens of thousands, times of millions of data, right? And all this data need to be labeled, and this really time-consuming, labor-intensive job. There are some ways that we can semi-automate the task. For example, there are researchers combining unsupervised and supervised learning together. So we can somehow using a subset of labeled data to figure out the model, and then use that model to do predictions, and then we can use the predicted value to serve as the input for another round of labeling. Or using unsupervised learning to cluster the different data types. So there are a variety of ways scientists are able to improve the efficiency of data labeling, but well, it's still a really labor-intensive activity and efforts. And for the second question, I think that there are no definitely different barriers in the US to adopt AI. So no, many, I would say probably many different aspects. One is whether the government is willing to lead the efforts. For example, in China, the central government made a lot of efforts to provide the investments and try to attract intellectuals to do machine learning, deep learning. Where in the US, it's mainly industry-led efforts, right? That's big companies or startup companies, they are doing most of the job. And we see recently there are trend that the US government is trying to, federal government is trying to lead some efforts. For example, last year they created the NSF large funding, and each fund is about several million to $60 million to ask universities and enterprises to apply for the funding to create centers and institutes for AI. I think that's a good start. But well, another barrier is really we as human beings, because we are sometimes reluctant to adopt this new technology. We are suspicious. We don't know what is AI. We don't trust the machine. And also a lot of ethical issues that are raised. So the picture is a lot more complicated than just advancing the technology alone. There are so many interrelated pieces.
Wonderful. Well, we have nearly made an hour go away. We know we can do that very quickly. And I want to pose a final question from Meng Meng, because I think it's going to take the discussion back to something that you feel passionately about and a good place to leave us. Meng Meng is wondering, how would AI transform public health and research? If we have all this massive data, do we need specific research questions, or do we just throw the research, the data into machine learning and we get all the answers? So where do we take this?
That's a great question. So I would say, no, probably we can work in a parallel fashion. So on the one time, on one sense, we definitely want to create research questions. We want to address really important, profound public health or social questions, and we think about how the machine learning, the AI technologies can facilitate our research or efforts. And second, we can also be technically savvy as well. No, we as public health researchers should really be open-minded and try to learn and adopt those new technologies, and then think about how those tools can be used to facilitate our research and to have a positive social impact. I think they are not contradictory to each other, but they really reinforce each other.
Perfect. Well, we are at time. Ruopeng, is there a final thought that you would like to leave this audience with before we call it a day?
Yeah, sure. First, I really appreciate all of you to come to the space to talk about this challenging topic. Some of the contents may not completely comfortable to some of you, and I try not to avoid those questions because I think they are challenging and we should discuss those questions. And this is only the beginning of the AI series of Open Classroom. We have 7 talks in total, so stay tuned and you are welcome to join our future conversation. And thank you so much, Shelley and Smriti, and thank you for our audience.
That's perfect. Thank you so much. This was a great launch to the series. Yes, to the audience, second Thursday of the month is when we're going to be doing this series, so you may want to specifically mark your calendar. Wonderful first talk, Ruopeng Sumeridi. Such a pro as a first-time moderator. So happy to be doing this with you. To our audience, thanks for great questions and being with us. We hope to see you again at another program soon, perhaps in this series or anything else we have going. Have a wonderful day, everybody. Take care and goodbye now.
Take care. Bye.